Okay, today for a change I'm going to go through a GCSE paper. It's the Physics Paper 1, which is also used in the Double Award Science for the Edexcel International GCSE, which we teach at the school where I work. Okay, so this is a combination paper made from a variety of paper ones, and we used it as a practice exam for our Year 10 students who are halfway through the course. So it covers topics 1 to 4, which is forces, electricity, waves, and energy. Okay? Alright, so the first question is about wave behavior. They have wave behavior on the left and diagrams on the right. And it says, draw one straight line from each wave behavior to the example, that best shows the behavior. So total internal reflection, and they want you to draw a straight line. Now, I don't know how strict they're going to be on that. Now, I'm not going to get a ruler out. So total internal reflection happens in the denser medium. So remember, total internal reflection is when the angle that it hits here is greater than the critical angle, and then it bounces off internally. So this one is total internal reflection. There's my straight line. Refraction happens when you go from one medium into another medium. So I have to show you the third diagram. So refraction is the bottom diagram. So it goes from air, again you draw the normal, and you see that the angle of refraction is smaller in the denser medium, which in this case is glass. So reflection, well actually this is reflection, but normal reflection is here, and that's why they've got an aluminium backing. Yeah, so it hits a mirror basically and reflects, and again the normal would be there, the angle of incidence in this case will be equal to the angle of reflection, just like in total internal reflection. So that's, you get 3 marks for each of these, 1 for the reflection, 1 for the refraction, and 1 for the total internal reflection if you've drawn them correctly. Question 2 says state 2 properties that all waves have in common. Well, rather than write them all down because there's multiple answers here, part B is any 2 from all waves can reflect, all waves can refract, and the idea that all waves transfer energy, and then in brackets, so you don't need the bits in brackets as long as you've got these keywords that you've shown that you know that waves transfer energy without transferring the matter. Okay, and all waves have amplitude, wavelength, or frequency. So they're accepting that. I haven't actually accepted this one in some of the answers, so maybe I need to go back and check if I've made a mistake when I was marking them. Okay, so that's what they will accept. And it's good for you to write all waves can reflect, all waves can refract. This is the mark scheme written for people marking the exams. Okay, so that's part B. I've then added in the part C because there was no question in no question on the wave equation in the questions I've chosen. So I took one from another question which we couldn't use because some of the content was from year 11, and I put it in there. So a radio receives a radio wave of frequency 93 megahertz. So you need to know what kilo, mega, and giga, for example, mean in terms of standard form. So this means the frequency is equal to 93 times 10 to the 6 hertz. So do you know what mega means? Then it says state the formula linking speed, frequency, and wavelength of a wave. And this year in GCSE they still gave you all the equations, so you just got to pick the right one. And speed equals frequency and wavelength. If you can remember how to use a triangle, to help you, the thing which is the 2 terms which are multiplied always go on the bottom. The thing which equals the 2 things which are multiplied goes on the top. Okay, so in this case, if you know the speed is equal to frequency times wavelength, that means you put your finger on V, which is the speed, then it gives you frequency times wavelength on the bottom. So that if they're next to each other, you multiply, and if it's over, it's like dividing. Okay? All right, so it then wants you to calculate the wavelength. The wavelength is lambda, so you need to know that that's lambda, that's f, and that's v. Okay? So v equals f lambda. So if you want to work out wavelength, it's, if you have the ability to remember the triangle, lambda is v over f. They will never give you the triangles, so you need to know how to mathematically change the subject of the equation. So lambda will be v over f. V is given to us here. Yeah, speed of radio waves is the same as speed of light. All electromagnetic waves go at this speed in a vacuum or in air, divided by 93 megahertz, which is 93 times 10 to the 6. And if you do it correctly, you will get 1 for substitution, 1 for making sure that you've got mega converted, and 1 for the answer being exactly 3.2. Two significant figures is what you should use, because here they have two significant figures and here they have two significant figures. So the data is only accurate to two significant figures. Okay. The next one is about upthrust, a boat floating on the surface. The boat sinks and therefore it creates the upthrust. It's a fact that the boat displaces, upthrust is due to the displacement of this amount of water, and the amount of the weight of the water that you displace gives you the upward force, which we call an upthrust. So the ship floats because of it. Okay, the upward force acting on the ship is called upthrust. They're giving you that. The force is shown on the diagram. Draw another labeled arrow on the diagram to show the other vertical force. Well, what's upthrust equaling to keep it floating? That means there's a balance force situation where it has to be weight. So if the upthrust is this size and you're balancing it against the weight, the arrow for the weight must be equal in length and opposite in direction to the upthrust. You can't call it gravity. They will not accept gravity. Gravity is a general word. So as long as to the eye they look like they're the same length, you will get the mark here, 2 marks. So 1 for labeling it correctly. Weight, which is a gravitational force. You can write gravitational force, but the common term for the gravitational force is weight. Gravity is a general term. Okay. Now, forces are vector quantities. What is meant by vector quantities is a quantity that has magnitude or size and direction. So 1 for saying magnitude or size and 1 for saying direction. That's how you get 2 marks. Give another example of a vector quantity. Well, it could be, they don't want anything else that's a force, so you can't give another force example. You could give acceleration, for example, which is due to a force. Yeah? Or you could give velocity. Yeah, so velocity is speed with direction. Or you could give displacement. And there may be others that you can put that they would accept. Okay? So as long as you know what a vector is and got another example, you will get your 5 marks for this question. Okay? Question 3 is about a truck traveling on a horizontal road. The driver sees an obstacle in the road and then applies the brakes. Yeah, so it gives him, he has a thinking time, which is his reaction time, and then he realizes he has to apply the brake. So first of all, what affects the thinking distance? The thinking distance is while it takes him time to react. So it's to do with the reaction time. And condition of tires does not affect his thinking. Mass of the vehicle doesn't affect his thinking. Neither does the condition of the road. The only thing that could affect his thinking is, of the answers given, is, for example, if he's tired or he's taken in some kind of drug, or in this case, the example they're given is alcohol. So the answer is B. Now, the next one, it's got 4 answers again, but which of these factors affects both thinking distance and braking distance? Okay, well, the conditions of the brakes only affects the braking distance, doesn't affect the time it takes for him to think, and therefore the time it takes for the condition of the brakes does not affect the thinking distance, okay, because he's not applied his brakes yet. It's before he applies his brakes. The condition of the road likewise only affects the braking, and the mass of the vehicle only affects the braking, doesn't affect his thinking. But the speed of the vehicle affects his thinking, because if his reaction time is longer, then because the car is moving faster, in the time it takes him to react, the speed of the vehicle will increase how much he travels while he's thinking about braking, while he's reacting. And of course, the speed of the vehicle means it has more kinetic energy, and the brakes have to work harder, so it takes longer for the brakes in distance to slow down the car. Okay, so that's the beginning of this question. This has got part B and C still to come. The truck then experiences a braking force of 46,000 newtons. So that's a braking force. State the formula linking work done. Yeah, so the work done by the brakes with the force they got multiplied by the distance equals the work done. Work done in joules is the force in newtons times the distance travelled against the motion while it's in motion, which is slowing down distance. Okay, the distance it takes to stop, the stopping distance, if you like, while it's the stopping distance, while it's braking. So you could call it the braking distance. Let's say braking distance. All right, so the truck has 59,000 joules of energy in kinetic, store, in the kinetic energy store, before the driver applies the brakes. Okay, so that's how much energy is built up, and that's the amount of work the brakes have to do, this much, to get rid of the kinetic energy if you want to slow down to a stop. The braking force does work, mechanical work, because it's force times distance, physical work, on the truck to reduce that kinetic energy store of 590,000 joules to zero. So the braking distance is defined as the distance required for the kinetic energy store to reduce to zero. In other words, you've used up all the kinetic energy when the brakes are applied. Calculate the braking distance. So I put it in a triangle up there for you, just so you can understand. So the braking distance is this, because you want the distance. So it's work, which is 590,000, divided by the force, which was 46,000 newtons. Okay, divide it and you'll get approximately 13 newtons. You could show it as 12.83, but then really you should only use two significant figures, because they give you the force to two significant figures and they give you the work to two significant figures. So that's how you can work out how many decimal places you should include or where you should round them up to. Okay, that's a good general tip for any physics paper. All right, part C, the brakes increase in temperature when the truck is braking. In other words, the brakes get hot because there is a lot of friction involved, and the brakes have a metal disc, and there's two heat-proof pads, friction pads, which clamp down on the disc which is attached to the wheels. So when you actually clamp on that disc, the pads get very, very hot. State the name of the energy store that has increased for the brakes. So increase in temperature is an increase in the thermal energy store. Now remember, they want you to talk in terms of stores. They will not accept heat. Heat, a bit like gravity, is a general term, and the store of energy is called thermal. Okay, if you look at the syllabus, it tells you what the different stores of energy you should be aware of and the terminology. It then says, state the method of energy transfer from the truck to the brakes. Well, the method of energy transfer, the mechanism by which the energy transfer was a mechanical energy transfer. Okay? Whenever a physical force is used, transfer, can't spell. Whenever a physical force is used over a distance, in other words, we're using work as force times distance, it's called a mechanical energy transfer. Okay? So you could be doing the work, or in this case, the physical work is being done by the brakes. Okay, and that's how you get your 8 marks. Okay, that's 3 questions done. I'll probably split this into at least 3 videos. Okay, state Hooke's law. It says, question 4. Extension must be directly proportional to force. So the extension must be directly proportional to force. Well, you can see this graph obviously isn't. Directly proportional would be a straight line graph. So I'm already giving the answer to the next part of this question. Yeah? Up to the limit of proportionality. They are accepting, it's near it, except elastic limit. The limit of proportionality is not exactly the same as the elastic limit. You can go a little bit beyond the limit of proportionality, which would be the straight line part of the graph, and it'll still return to its original shape. So the elastic limit is slightly further on the graph, technically speaking, than the elastic limit. So you get 1 mark for saying that the force and the extension are directly proportional up to the limit of proportionality or the elastic limit for the second one. The graph then shows how a rubber band extension of a rubber band varies with force. Now you can see this, the rubber band, which you should have in your notes if you've got a complete set of notes from this topic, this one forces, is not a linear relationship. Explain how the graph shows that rubber does not obey Hooke's law. Well, the line is not straight, yeah? So the force is not directly proportional to the extension, which Hooke's law requires, okay? So as long as you got words that explain that you know it must be a straight line and it's not, and that you then say, well, if it's not, it can't be directly proportional, and directly proportional, as we've defined above, Hooke's law requires this. Yeah? So that's further clarification of how to get the marks. Okay. The next part, they're using a rubber band in this model aeroplane, which is powered by a rubber band. Okay. Basically, you twist the rubber band and it stores some kind of elastic potential energy. Person rotates the propeller, yeah, of the model aeroplane. So basically, you're turning it, yeah, rotating it. This twists the rubber band. He then releases the propeller, yeah, and it starts spinning. So as it starts spinning, it's going to produce a forward thrust, won't it? The spinning will produce a thrust. And energy transfer occurs, yeah. Why? Because I suppose the propeller is working against the air, yes? Energy transfer, therefore, would be mechanical. Because it's working against the air, we have force times the distance involved. And this box lists words associated with energy. There's 9 of them, and there's 3 blanks to fill in. Use words from the box to complete the passage. The person does mechanical work to work against the elastic band, to twist the rubber band. So that takes physical work, therefore it's mechanical. As the person twists the rubber band, it extends, yeah, the rubber band extends, increasing the elastic store of energy, or the elastic energy store of the rubber band. When the rubber band is released, it then does mechanical work itself, increasing the kinetic energy store of the propeller. Yeah. Now over here, they're also accepting potential energy because if it's a good plane, when it starts moving, it should also gain in height. And a gain in height, yeah, the kinetic will lead to the gain in height. But really, it should be kinetic because this is stored in the propeller. The propeller is rotating. Okay. Hope that makes sense. It says show the mark scheme. Let's see if I can do that for you. We're talking about question 4. So there is all of the mark scheme for question 4. Yeah. And the green is my notes. So mechanical, elastic for the first 2 points, and then they're allowing gravitational or kinetic for the third point. I think that's a bit generous. I would have put kinetic only. And you can look at part C as well if you want to go and freeze the video for the final part, which I'm going to do now. Okay. For the final part, part C, it says diagram 2 shows the aeroplane flying horizontally. That means it's not gaining height if it's flying horizontally to the right. So the right means the propellers are thrusting it forward, okay, by working against the air. The aeroplane flies at a constant speed. That means it's not speeding up. That means the forces must be balanced forces. And obviously speeding up is in the horizontal direction as well. Okay, so it's not gaining height and it's not gaining speed. So we're talking about balanced forces all round. So diagram 2 shows two forces, the lift and the thrust. And they want you to draw labeled arrows on diagram 2 to show two more forces acting on the airplane. Well, two more forces will be weight and drag. You get 2 marks for each. Well, what do you think? Same as before. If it's balanced forces, the weight downwards, and remember you can't use gravity, the arrow must be equal length. So you get 1 mark for weight, 1 mark for the length of the arrow. Just likewise, thrust is about that length. So the drag is opposing it. So I'm trying to make sure to the eye, the drag force, you can also call it air resistance, the arrow length are equal but in opposite directions. So if you got equal arrows and the drag, 2 marks for this and 2 marks for that will give you the 4 marks. Question 5. Question 5 is about a table tennis ball, a very light plastic ball filled with air. A student drops the table tennis ball from rest. That means initial velocity is 0, that's u. The ball falls 13 meters, okay? So if it's dropped, its u is 0. It tells you it's 13 meters to the ground. So that's s, yeah, in the Suvat equations. Show that the final speed, v, yeah, just before it reaches the ground, should be around 16 meters per second. So they want you to show this. Yeah, so they don't want you to use this data, they want you to calculate that you can get v, final speed, equal to 16 meters per second, using this equation, v squared equals u squared plus 2as, where a, because it's falling to the ground, is gravity, which is given to you on a data sheet as 10 meters per second squared. So every second that's in the air, in the 13 meters that it falls, it will speed up by 10 meters per second squared. Okay, so we know u is 0, so you put 0 in. 0 squared obviously is still 0. 2 times a, which is 10, and s, which is 13, you put those in. 0, so if you don't put anything in for v squared, you do that, and you see it's 2 times 20, or 130 times 2 is 260. You then square root the 260, and you get 16. So 1 for putting the numbers in, 1 for realizing that you need to square root it, and 1 for showing that 16.1 is approximately equal to 16 meters per second. Okay. The student then suggests that the ball will reach the ground with a speed less than 16 meters per second because of air resistance. Now, of course, that's true. So all these equations, like this equation, these are only work under constant acceleration. And constant acceleration is not always the case if something is very light. So a very light plastic ball will easily be affected by air resistance. So you have to use your knowledge and ideas about forces to explain 5 points you need to explain to justify the student's suggestion. Okay, so how do you verbalize this? And I think these are the questions students find the most difficult to answer. Okay. Here's the mark scheme. You can see part A, which I've already given to you, and part B. So here's the point. You first need to say the downward force, the ball has weight, yeah? And initially, while it's falling, yeah, just at the beginning, the only thing that you have is weight, okay? Weight is downwards. There's no opposition force. So the ball will accelerate due to the weight initially, okay? But then the drag increases as the ball speeds up. Yeah. So as the ball speeds up, it's accelerating, so the ball speeds up, and drag force increases with speed. So by the time you've got a little bit of speed, the weight doesn't change, but you have a little bit of drag. And initially the drag is smaller than the weight, so it will the drag opposes the weight. I've said that they should accept that as an alternative way of wording this. The drag opposes the weight initially, yeah, and the resultant force decreases. So W minus D here is less than W minus 0 there. Okay, so the resultant force here is W, and then the resultant force is less over here because it becomes W minus D. Okay, so the acceleration decreases. Okay, so there's a fifth way of getting the mark. Eventually, when the drag, as it speeds up even more, the drag will equal the weight, and the resultant force becomes 0 because the forces then become balanced. So the third force diagram, W doesn't change, the weight is constant, and now the drag will get to a point where you have balanced forces. At this point, we say there is no more acceleration, so it's reached its final velocity, otherwise known as terminal velocity, or it will continue at constant speed. Okay, the acceleration, in other words, becomes 0. And that's how you've got to be able to explain things in physics that clearly. Okay, so all of that needs to go in here, and you need to put them in bullet points so it makes it easier for the examiner to mark your work. Okay, basically you're just being logical. All right, so we've done forces. The next question is on electricity. So I think the next couple of questions are on electricity. So here you have a circuit showing a light-dependent resistor, which is this symbol, and called an LDR. Let's write that in there. So LDR. And this is just a normal resistor, which has 73 ohms, and a 73 ohm resistor connected in series with a 1.5 volt cell. So basically the 1.5 volt cell the 1.5 volts the cell is providing is being shared by the LDR and the resistor. Okay, complete the diagram by adding an instrument to measure voltage, which is a voltmeter, to measure the voltage of the LDR. So to measure the voltage of the LDR, remember, you need two wires to go across the LDR. Across means in parallel with. So the voltmeter doesn't actually go in the circuit, doesn't go in series with the circuit. Well, if they said add an instrument to measure the current in the circuit, then you would put an ammeter in the circuit, and you can put it anywhere. Okay, because the current is 7.8 milliamps throughout, and remember this is milliamps. Okay, all right, so once you got that, you get 2 marks for the symbol and making sure that it's in parallel with the LDR. State the formula linking voltage, current, and resistance. Ideally, you should write full word equations. Okay, symbols wise, V is voltage, I is current, and R is resistance. The unit for resistance is ohms. Okay, so the current in the circuit, it says, so you get 1 mark just for making sure you got the right equation written down. Okay, the current, so we don't use C for current. Okay, you have to remember I is current. Okay, V equals IR. All right, so this is how you put in a triangle. Yeah, just while we're explaining the question, but they won't give you the triangle. Remember, I told you that before. Current in the circuit is 7.8 milliamps. That means I is 7.8 times 10 to the minus 3. So milli equals 10 to the minus 3. Okay, just like millimeter, you have 1,000 of them in a meter, so it's 1,000th. So calculate the voltage across the 73 ohm resistor. Well, the current is also going through there, 78 milliamps. Oh, 7.8 milliamps. So 7.8 milliamps is going through there. The current's the same everywhere in a series circuit. So they want to see that you know the circuit rules. So if we know the current is 7.8 milliamps, you have to put it in standard form, multiply the resistance, V equals IR, and you'll get 0.57 volts. Why are we putting 2 significant figures again? Because everything they give us is 2 significant figures, 2 significant figures. two significant figures. So this will be the accurate value on your calculator, and you got to decide what to round it up to. And I'm telling you, if the data given is 2, the answer here should be 0.57, and they've been kind, they've given you the units. That's why it's only 2 marks. 1 for that, 1 for that. If you don't get the conversion right, they might give you 1 mark for doing the correct maths. So remember that the resistance is shared. The voltage of the cell, which is 1.5 volt, is the total voltage of the circuit, is shared between the voltage across the LDR and the voltage across the fixed resistor. So if the fixed resistor has 0.57 volts, how much of the 1.5 is left for the LDR? So remember, this plus 0.57 must equal 1.5. So if you want to write that, it follows that 1.5 must be equal to the voltage across the LDR plus 0.57, which we just worked out. So changing it around, you'll see it will be 0.93 volts left. Yeah, again to two significant figures for the LDR. Okay, so this is voltage is shared in series circuits. The next one, it shows a graph, shows how the resistance of the LDR changes with light intensity. So why does that happen? As you increase the light intensity, that reduces the resistance. See, as you're going this way, the resistance goes down. So the resistance decreases, but in a non-linear way. It's not a straight line decrease. They want you to say it's in a non-linear way. They want to give you more. They want you to give more detail than just say it decreases. So 1 mark for saying it decreases, 1 mark for realizing that it's a curve. Okay, so as a curve or at a decreasing rate. Okay, I'm accepting inversely proportional, but it may not be inversely proportional. Inversely proportional means if you double the light intensity, the resistance will halve. I'm not sure whether that's correct, but at this level, I think that would be an alternative way to realizing that you have a little bit more detail in your answer than just saying it decreases. So the resistance we know decreases of the LDR. So our LDR goes down. You shouldn't write it like this in the exam. You should make sure you write it out in full. So what will the effect be on the current if that decreases? Well, if the resistance decreases, the current will increase because the total resistance in this circuit, if this resistance goes down, this one doesn't change, the total resistance will decrease. That means if there's less resistance in total to the voltage, the current should go up. The total current should go up. That means the current through both of them will go up. Okay? So you need to put it like this. The current will increase. That's all they're looking for. Just because it says state means you don't have to explain it. So that's where you get your 1 mark from. It then says explain why the voltage, in this case, why the voltage across the LDR actually decreases. Now, so if you think about it, if you got a voltmeter across there, and this becomes less resistant, remember they share the voltage according to their resistances. If this has gone down and this has stayed the same, this will get a bigger ratio or a bigger percentage of the 1.5. This will be left with a lower percentage or a lower ratio of the lower share of the 1.5 volts. Basically, the one with a higher resistance gets more of the voltage according to the resistance. So in a series, this is how I explain it. So explain why the voltage across the LDR decreases when the resistance of the LDR decreases. Okay, so in a series circuit, the voltage of the cell is shared by the two, in this case, resistor components according to their resistance. That's how I explain it. So as long as you can explain that you know that, that's 1 mark. Since the LDR resistance decreases, it will get a smaller share of the total voltage. I think this is the best way of doing it. However, the examiner has put it in a different term. So the current has gone up, we know that. Larger current means larger voltage across the fixed resistor. Yes? So the fixed resistor gets a larger voltage, the total voltage remains the constant, therefore the voltage left over will be less for the LDR. So I've added my own opinion here, or voltage of a component is proportional to its resistance in a series circuit. Okay, because you know that voltage is shared in a series circuit and the total voltage remains constant. So there's different ways of communicating that. Hopefully you'll have a good examiner and they'll understand what you've said. Okay, the next question shows a Van der Graaf generator, which you don't have to do in the combined science course, double science, except you do need to know these questions. So the diagram shows a Van der Graaf generator, which is designed to provide high voltages. So to produce high voltages, this one actually becomes positive, and this one will be neutral or negative. Okay, it'll be neutral. So relatively, this will be positive and this one will be negative compared to each other. The unit in voltage is called the volt. Which of these units is a volt? Coulomb per second? No, coulomb per second is equal to amps. Yeah? Joules per coulomb? Yes, that's the one, is equal to volts. Joules per second is watts. Yeah? And newtons per coulomb you haven't met in this course. It's a field strength. Okay, so if you don't know it, you've got to go with what you know. Okay, this is to do with field strength of something. So B is the answer. It then, so we know is joules per second, as joule per coulomb. So voltage is joules per coulomb, and it wants you to now link a formula between voltage, energy, and charge. Okay, so can you state the formula linking energy transferred, voltage, and charge? Well, up to this year, after COVID, they have been giving the equation sheets. So you've got to find the right one. And there's one called energy transferred equals voltage times charge. Yes. I like to write it Q times V. Q is charge, V is voltage. Okay. So energy is in joules, this is in coulombs, and this is in volts. And if you change that into a triangle, yeah, remember the two that multiply go at the bottom. So if you want to know voltage, you can see it's energy over charge, so it's joules per coulomb. Yes? Remember, energy is in joules. Joules, volts, coulombs. Okay? So symbol is Q, it's measured in coulombs. Symbol is V, measured in V. Energy in joules. Okay, so don't get confused between the words which define it, charge, the symbol which is used, and the units which is used. You need to remember all three. Then it says calculate the energy transferred, E, when it passes through a voltage of 150 kilovolts. That's 150,000 volts. Okay, so they're telling you kilovolts. Again, you need to know these prefixes. So you know kilo from kilogram, 1,000 grams. Yes, kilometer, kilometer, 1,000 meters. So you already know them, you just need to make sure your thinking is clear. They're giving you the charge of an electron. So when they calculate the energy transfer to an electron, which has this much charge, tiny amount of charge, when it passes through a voltage of 150,000. So if you want an electron to speed up, you put a positive plate in front of it, and if the plate is 150,000 volts, it will speed up quite a lot. Yeah? Okay, so it's going to gain an energy, but how much? This is how much kinetic energy it will gain. So you put the charge of the electron, Q, multiplied by the voltage you're putting 150,000, multiply 2, and you'll get the answer again to two significant figures. Okay, so you get 1 mark for converting it to 150,000, 1 mark for multiplying the two numbers correctly, 1 mark for the answer as well. Okay. Part B, the Van der Graaf generator is fully charged. When the Van der Graaf generator is fully charged, it can store this much charge in total, 2.9 times 10 to the minus 8 coulombs of charge. Again, two significant figures given in most of these questions. State the formula linking charge, current, and time, where charge is current times time. Q equals IT. Remember, Q is in coulombs, I is in amps, and T is in seconds. Okay? As a triangle, Q would go on the top because it's the one which represents charge. I times T, you multiply to get it equal to Q. The charge on the generator, Van der Graaf generator they're talking about, discharges through the air as a spark. So if there's a gap, it can jump across the gap as long as the voltage is high enough. Okay, that's what lightning is. So the charge takes a time of 0.68 milliseconds. So you already know what a millisecond is. It's a thousandth of a second. So t is 0.68 times 10 to the minus 3. Don't forget, it's already less than 1. Okay? If you're trying to move the decimal place forward, make sure you don't make a silly mistake. Calculate the mean current, average current. Well, I, yes, is Q over T. So I is Q over T. The charge is given to us at the top of the page, 2.9 times 10 to the minus 8 coulombs, divided by the time, which should be in seconds. So don't forget times 10 to the minus 3, 1 for converting it, 1 for putting the right numerator and denominator, and then 1 for getting the answer. So 4 significant figures will come to something like this on your calculator. But why should you write it out? Because all the data we're given is 2 significant figures, and you can leave it in standard form. That's the most adult way, physics-wise, of showing your answers. Okay? So that's the end of question 7, and I'm going to pause at this stage, have a break, and then come back and do question 8 onwards. I hope you found it useful. So this is going to go on my YouTube channel. Most of you, if I teach you, already know about it. So when you're going through this in class, I expect you to go through your mistakes and to write them out in a purple colored pen to improve your communication skills. Okay? So you will have noticed that the attention to detail is what gets you all the marks. So if you found it useful, please like the video. Share it with any friends who are doing the same exam as you so I get some more subscribers. And subscribe if you haven't, because it will tell you when the second part of this video is shown. And if you look in the playlist, there's a GCSE playlist. You can find other GCSE tests I put on there used for different classes. So it allows you to revise for next year as well. And next year we'll put more videos on there as we build up to the mock exams and then to the final GCSEs as well. Okay, so hopefully see you in the next video. Bye for now.